Carl Friedrich Gauss, often hailed as the Prince of Mathematics, was a towering figure whose genius left an indelible mark on nearly every field of mathematics and science. Born on April 30th, 1777, in Brunswick, Germany, his origins were humble, a stark contrast to the monumental intellectual heights he would later achieve. His father, Carl Friedrich Gauss, was a man of many trades, a gardener, a butcher, and a bricklayer, who, while honest and hard-working, did not initially recognize the full scope of his son's prodigious talents. His mother, Dorothea Benz, was a woman of sharp intelligence and strong character, and it was she who fiercely supported her son's intellectual pursuits, recognizing the spark of genius in him from a very early age. Gauss's precocity was the stuff of legend, with tales of his extraordinary abilities surfacing from his toddler years. At the tender age of 3, he corrected a complex payroll calculation made by his father, a feat that foreshadowed the computational wizardry that would define his career. The most famous anecdote of his youth occurred when he was just 8 years old, in a busy arithmetic class. His teacher, G. Büttner, hoping to keep his students occupied, assigned them the laborious task of summing all the integers from 1 to 100. Almost immediately, while his classmates toiled away, young Gauss placed his slate on the teacher's desk, proclaiming, "There it is. He had not performed the tedious addition, but had instead discovered a profound mathematical pattern. The sum was simply 50 pairs of numbers, each adding up to 101, 199, etc. For a total of 5,050. This incident brought his phenomenal talent to the attention of Martin Bartels, a teaching assistant who shared a passion for mathematics and became a crucial mentor to Gauss. Through Bartels' connections, Gauss was introduced to Karl Wilhelm Ferdinand, the Duke of Brunswick, a pivotal moment in his life. Impressed by the boy's intellect, the Duke became his patron, generously providing financial support for his education, freeing Gauss to dedicate himself entirely to his studies. Gauss attended the Collegium Carolinum from 1792 to 1795, where he devoured classical languages and advanced mathematics with equal veracity. It was during this period that he began to formulate his groundbreaking ideas in number theory, a field that would become his lifelong passion. He independently rediscovered several important theorems, including the law of quadratic reciprocity, a cornerstone of modern number theory. In 1795, he left for the prestigious University of Göttingen, one of Germany's leading centers of learning. The years at Göttingen were among the most productive of his life, marked by a series of extraordinary breakthroughs. A pivotal discovery came in 1796, a year he called a year of jubilee for himself and for mathematics. On March 30th, he proved that a regular heptadecagon, a 17-sided polygon, could be constructed using only a compass and straightedge. This was a monumental achievement, as the construction of regular polygons had been a famous unsolved problem for over 2,000 years, since the time of the ancient Greeks. This success was so profound that it convinced Gauss to dedicate his life to mathematics rather than philology, his other great love. He was so proud of this result that he requested a regular heptadecagon be inscribed on his tombstone, a wish that was ultimately not fulfilled due to the difficulty of the task for the stonemason. In 1799, Gauss completed his doctoral dissertation at the University of Helmstedt, in which he provided the first widely accepted proof of the fundamental theorem of algebra. The theorem states that every non-constant single-variable polynomial with complex coefficients has at least one complex root. While others had attempted proofs before, Gauss's was the first to be considered truly rigorous, and he would go on to develop 3 more distinct proofs of this theorem over his lifetime. The year 1801 marked another milestone with the publication of his magnum opus, Disquisitiones Arithmeticae, Arithmetical Investigations. This seminal work revolutionized number theory, organizing and expanding upon the work of his predecessors like Fermat, Euler, and Lagrange, and adding a wealth of his own original contributions. In it, he introduced the concept of modular arithmetic, a system of arithmetic for integers, which has become an indispensable tool in modern mathematics and computer science. The Disquisitiones was written in Latin, the scholarly language of the era, and its dense, rigorous style made it challenging for many of his contemporaries to fully appreciate at first. It was a work for the ages, laying the groundwork for number theory for the next century and beyond. Also, in 1801, Gauss's genius turned towards the heavens when the Italian astronomer Giuseppe Piazzi discovered a new celestial body, which he named Ceres. Unfortunately, Piazzi could only observe Ceres for a few weeks before it was lost in the glare of the sun, and the astronomical community was left with insufficient data to predict orbit. Many of the greatest mathematicians in Europe tried and failed to calculate its trajectory from the sparse observations. Gauss, then 24, took up the challenge, armed with a powerful new mathematical tool he had developed, the method of least squares. This statistical method allowed him to determine the most probable orbit from the limited and error-prone data. In a matter of weeks, he produced a prediction for Ceres's location that was remarkably accurate. On December 31st, 1801, the astronomer Franz Xaver von Zach rediscovered Ceres precisely where Gauss had predicted it would be, a triumphant validation of his method. This achievement brought Gauss international fame and cemented his reputation as a mathematical genius of the highest order. It also led to his appointment in 1807 as professor of astronomy and director of the Astronomical Observatory in Göttingen, a position he would hold for the rest of his life. While his work in astronomy was significant, Gauss's heart remained with the queen of mathematics, number theory. He once remarked, "Mathematics is the queen of the sciences, and number theory is the queen of mathematics." Gauss's personal life was marked by both happiness and profound tragedy. In 1805, he married Johanna Oster, with whom he had 3 children. He described her as his angel, and their marriage was a source of great joy. Tragically, Johanna died in 1809, following the birth of their 3rd child, Louis, who himself died a few months later. This loss plunged Gauss into a deep depression that would haunt him for years. He married again the following year to Minna Waldeck, a friend of his first wife, and they had 3 more children. While his second marriage was not as happy as his first, it provided a stable home life that allowed him to continue his work. Throughout the 1810s and 1820s, Gauss's interests expanded into new domains, including geodesy, the science of measuring the Earth's shape and size. He was commissioned to conduct a large-scale geodetic survey of the Kingdom of Hanover, a massive undertaking that occupied him for many years. This practical work led to significant theoretical advances, particularly in differential geometry and the study of curved surfaces. His Theoria Egregium, remarkable theorem, was a landmark result, proving that the curvature of a surface is an intrinsic property that can be determined entirely by measurements made along the surface itself. This concept would later become absolutely fundamental to Albert Einstein's theory of general relativity, which describes gravity as the curvature of space-time. To aid his survey work, Gauss invented the heliotrope, a clever instrument that used a mirror to reflect sunlight over great distances, allowing for highly accurate triangulation. During this period, Gauss also began to secretly explore the possibility of non-Euclidean geometries. For centuries, Euclid's 5th postulate, the parallel postulate, was considered an unassailable truth, but Gauss realized that consistent geometries could be built without it. He was hesitant to publish his findings, fearing the controversy and ridicule from the established mathematical community, which he referred to as the clamor of the Boetians. Thus, the credit for the discovery of non-Euclidean geometry went to Janos Bolyai and Nikolai Lobachevsky, who published their work independently a few years later. In the 1830s, Gauss's focus shifted once again, this time to physics, particularly magnetism and electricity. He collaborated with the physicist Wilhelm Weber, a partnership that yielded remarkable results. Together, they organized a worldwide network of magnetic observatories to systematically measure the Earth's magnetic field. In 1833, they invented the first practical electromagnetic telegraph, connecting the observatory to the Physics Institute at Göttingen over a distance of about 1 kilometer. This device predated Samuel Morse's more famous invention by several years, though Gauss and Weber saw it primarily as a scientific instrument rather than a commercial product. Gauss's work on potential theory, stemming from his studies of gravity and magnetism, led to what is now known as Gauss's law, a fundamental principle of electrostatics. This law, along with his law for magnetism, would later be incorporated as 2 of the 4 famous Maxwell's equations, which form the complete foundation of classical electromagnetism. Gauss was known for his relentless pursuit of perfection, and his motto, pauca sed matura, which means few, but ripe. Yesta, analytical. He was often unwilling to publish a result until he was completely satisfied with its proof and presentation, believing that a work should be finished and polished, with no trace of the scaffolding used to build it. This perfectionism meant that a significant portion of his discoveries were never published during his lifetime and were only found in his personal diaries and notebooks after his death. These posthumous revelations included his work on non-Euclidean geometry, complex analysis, and even an early version of the fast Fourier transform algorithm. Despite his towering intellect, Gauss lived a relatively simple and conservative life, deeply attached to his home in Göttingen and the Kingdom of Hanover. He was a monarchist and held conservative political views, a man of the old world who happened to possess a mind that saw into the future. In his later years, he suffered from gout and increasing loneliness, but his mind remained sharp and active. He continued to work and lecture until shortly before his death. Carl Friedrich Gauss died peacefully in his sleep in Göttingen on February 23, 1855, at the age of 77. His brain was preserved and studied, and it was reported to have an unusually large and convoluted cerebral cortex, a physical hint at his extraordinary mental powers. His legacy is monumental and all-pervasive, from the normal distribution in statistics, the Gaussian curve, to the unit of magnetic flux density, the Gauss. His name is woven into the very fabric of modern science. He was a true colossus of the intellect, a man who advanced mathematics in a single lifetime more than most could in 1,000 years, rightfully earning his title as the Prince of Mathematicians.